So we can use X-ray crystallography to look at these long-range orders of atoms. And we call that a crystalline lattice. It's the regular arrangement of atoms within a crystalline solid. And so atoms can be arranged in different ways, and which way they choose is going to be the one that minimizes their energy. They're going to go together in a way that minimizes their energy. And this is a lot like putting marbles into a box or anything round, packing fruit into a box. It's going to naturally go in a way that allows those spherical objects to be close together and towards the bottom, right? They're not going to stack up in little piles. They're all going to fall to the bottom. It's this lower energy. So when we look at how these are arranged, we talk about unit cells. And a unit cell is the smallest part of this crystal that if we reproduce it, repeat it over and over again, we get the overall pattern. So in this illustration, this pink square here, if I take that and copy it here and here and here and just keep copying it, it'll give me the overall pattern. The circles here represent lattice points. That's going to be a place where there's an atom, an ion, or a molecule, and that's the unit cell. So there are cubic unit cells. Cubic unit cells have equal edge lengths and 90-degree angles. So this is a cubic cell. This is not cubic because the lengths here are not all the same. This one's orthorhombic. So there's all these different names. The only ones we're going to look at are cubic and hexagonal. I'm not sure why they showed you all of those. You can get into the study of crystals and you can find naturally occurring substances that have all of these different arrangements of their atoms. And that's why some crystals make little cubes. Like if you go home and you look at the table salt in the shaker. Have you ever looked at that closely? They're little cubes. Does Martin do that on purpose? No. Salt does that naturally. It will just naturally form cubes. So we're going to look at unit cells in a relatively simple way. We're going to look at them in such that every atom is the same as the other atoms. So we're not going to be worrying about we've got two different kinds of ions or anything. So when we look at these cells, there might be different colors, and we're just using different colors to help us identify and visualize what's going on here. They're all going to be the same atoms. So a couple of numbers that we attach to these unit cells. One is a coordination number, and that's the number of atoms that each atom is in direct contact with. So the number of nearest neighbors. And that's important because those are the atoms that can be interacted with. The interactions between atoms are dispersion forces, and those only occur at very short distances. The other thing that's important is the packing efficiency, which is the percentage of the entire volume that is actually occupied by the spheres. So if you think about packing a box of oranges to ship somewhere, I think a lot in terms of fruit because that's a big deal where I live. So you pack oranges, you want to get as many oranges in the box as possible, right? You don't want to be shipping off a whole bunch of air. You want that to be full of oranges. So packing efficiency gets more oranges into the same size box. And these two go hand in hand. If you have a high coordination number, you're going to have a larger packing efficiency. Okay, so these are three different cubic cells. The simple cubic, body-centered cubic, and face-centered cubic. We'll look at number of atoms per unit cell, the overall structure, the coordination number, the packing efficiency, And then we can also, using geometry, identify the edge length. How long is a side in terms of the size of the atoms? So we'll look at each of these individually. So the simple cubic cell has an atom at each corner. So here we've cut away, and this is just the simple unit cell. And so it's going to be 1/8 of this atom, and 1/8 of that atom, and 1/8 of this, and 1/8 of that. And so we have 8/8 of atoms, right? So if you took all these pieces and put them back together, that would equal 1 atom, right? If you take this unit cell and copy it over and over again, then you'll end up with whole atoms, right? And so you might say, well, why can't you just say that the unit cell is 1 atom and reproduce that? Well, because that's not going to give you the same structure. So on this cell, the atoms touch on the edges, and so we can see that the edge length here is 1 radius plus the other radius, so it's 2 times the radius of the atom, whatever size the atom is. Any questions? So there's that unit cell. Here's drawing it with the whole atoms around it. And then here we're looking at sort of, we've pulled it apart a little bit so we can see better. We're looking at this atom here on the corner of one of the unit cells and seeing how many other atoms does it touch. 1, 2, 3, 4, 5, 6. It's touching 6 other atoms. So that's its coordination number. You can calculate the packing efficiency by calculating the volume of the cube. You know that the edge length is 2 times the radius. So that edge length cubed is the volume of the cube. And there's 1 atom in there, and you know the radius of the atom, so you can calculate the volume occupied by atoms and take a percentage to find the packing efficiency. So 52%, not super efficient. About half empty space. So let's calculate a packing efficiency, but here we're going to stay with 2 dimensions instead of 3 dimensions, make it a little simpler. So here we have a 2-dimensional representation of that simple cubic cell, where these guys are lined up so that their centers are in a straight line. And so we've got rows and columns, right? So packing efficiency, here we're talking about area instead of volume. So the efficiency is going to be the area of the atoms divided by the total area times 100 to make it a percentage. So if we look at this smallest unit cell here, how many atoms are represented? Here's a quarter atom, and there's a quarter, and another quarter, and another quarter, right? So those 4 pieces have the same area as one of the circles. You see that? What's the area of a circle? Pi r squared. So the area is pi r squared. We're not told what the radius is. That's okay. We'll just, do what we can. So that's the area of the atoms. So that's pi r squared. What's the total area represented by this white square? The area of a square is equal to the length of the side squared, right? The length times the width. Well, we look at this, and how long is one side? It's 1 radius, 2 radii, right? So L equals 2 times the radius, So 2 times the radius squared, so that's going to be 4r squared. Make sense? So pi r squared divided by 4r squared. So what happens to those r squared? They cancel out. Phew, because we didn't know what r was. Turns out it doesn't matter what r is. The packing efficiency will be the same. So pi is 3.14159, goes on, not repeating forever. Don't use 3.14 as an abbreviation. Your calculator has a button that says pi on it. Use that button. So you find your pi button. Wouldn't it be great if a pi button actually brought you pi? I think that'd be awesome. I can't find my pi button. There it is. Okay. So pi divided by 4 times 100, 78.5. So in this square, 78.5% is occupied by the purplish circles, and the rest of it's empty. That percentage applies to the whole thing. Any questions? So a body-centered cubic, it's also a cubic unit cell. The angles are 90 degrees, and the length of each edge is the same. But now we have one atom in the center. That's what it means by body-centered. And then we have 1/8 of an atom at each corner. So now the atoms are not touching along either the length here or the diagonal on a side. They're touching diagonally across the cube. So from this point, this corner, through the center one over to here, they're touching. So we don't have to examine the geometry, but there's the derivation if you're interested. The length is equal to 4 times the radius divided by the square root of 3. I don't expect you to remember that. How many atoms are represented in this cell? 2. The one in the middle, you can see that, the yellow one, and then the 8 corners. Each corner is 1/8 of an atom. So there's 2 atoms. So if we fill in the rest of those guys around here, it looks like this. And then when we try to get the coordination number, this is where you really have to be able to visualize in 3 dimensions. It's 8. Packing efficiency goes up 68% instead of 52. You don't have to memorize packing efficiency either. Okay, so we can do problems such as this one. An atom has a radius of 138 picometers. Okay, well, I'm going to write that down. Radius equals 138 picometers. And it crystallizes in the body-centered cubic unit cell. What is the volume of the unit cell in cubic centimeters? Well, let's think about a cube, right? How do we find the volume of a cube? It's length times width times height, and they're all the same, right? We'll call it L. So the volume of the cube equals L times L times L, L cubed. So to find the volume of this, if we know the radius of the atom that makes this up, we need to know the edge length in terms of the radius. And that's what was given over here. Right here. So for this cubic, body-centered cubic, L is 4r over the square root of 3. L equals 4r divided by the square root of 3. I guess I lied to you when I said there wasn't much math in this chapter. I forgot about this part, sorry. Well, we know what R is, right? So we could plug that in here. But we're not really looking for L, we're looking for the volume. So volume is L cubed, which means that we've got 4R over the square root of 3 cubed. The unit we're looking for is cubic centimeters, and we're starting with picometers. Personally, I find it easier to convert units before I cube them instead of after. So I'm going to look ahead and think, you know what, I'm going to put my radius into centimeters first and then stick it into the equation. So I want to convert picometers to centimeters. They both have a prefix, so I'm going to have 2 steps. So I'm going to go from picometers to meters first, and then from meters to centimeters. It's an extra step, but it's easy, and it always works. So what does pico mean?
-11.
10 to the minus 12. So other than things like centi and deci, most of them are 10 to the power, and that power is a multiple of 3. So 3, 6, 9, 12, 15, 18. Those are the numbers you can guess at. 10 to the minus 9 is nano, and pico is smaller than that, and so that's how I remember that it's minus 12. So 1 picometer is 10 to the minus 12 meters. And then centi, we should remember, centi is 10 to the minus 2. So 1 centimeter is 10 to the minus 2. So 1.38 times 10 to the minus 8 centimeters. So now I'm going to take that and plug this into this equation. 4 times 1.38 times 10 to the minus 8 divided by the square root of 3 cubed. So you got to be a little careful when you do this on your calculator. So we got 4 times 1.38 times 10 to the minus 8 divided by the square root of 3, and that whole thing to the 3rd power. Yeah, I screwed up. There we go. 3.24 times 10 to the minus 23rd. And the unit is cubic centimeters. That's a really small number. Should it be small? Yeah. This is a cube that contains 2 atoms. It should be really, really small. Any questions? Another one is the face-centered cubic cell. So here we have atoms that are centered on each of the faces. So there's half an atom here, and there's half an atom there, and half, and half, and half, and half.
So 3 whole ones.
There's actually 4 whole ones. Because this and this is 1, and this one and this one over here are 2, and then this one and the one on the bottom are 3, plus the corners. Yeah, so 4. And so these now are touching along the diagonal, and so we know this diagonal given as B here is 4 times the radius, right? So we've got this 1 radius and 2 radii there and another one, so that's 4r. And so you can use the Pythagorean theorem and find out that the edge length is 2 times the square root of 2 times r. There's going to be a total of 4 atoms in there. Now, when you draw the full atoms, it's getting a bit complicated looking. And that's why we're showing different colors to help you see where things are. These would all be the same atom, though, same element. So then when you go over here and you look at the coordination, it's actually really hard to count in there, but you just take it, believe them, it's 12. And if you calculate the packing efficiency, it's 74%. So we could do a problem like this as well. Chromium crystallizes with a body-centered cubic unit cell. The radius of a chromium atom is 125 picometers. Calculate the density of solid crystalline chromium in grams per cubic centimeter. The density of a metal depends on how those atoms are put together, right? Because you can't pack spheres without empty space. So body-centered cubic, the radius of the atom is 125 picometers. This has messed me up in lecture before because it's coming after we talked about face-centered, but this is about body-centered. So you use L equals 4r, yeah, over the square root of 3 is the edge length. So we want density. What's density? Mass over volume. So density is the mass of the cell divided by the volume of the cell. Well, we just calculated a volume of the cell, right? We converted picometers into centimeters. So you can do that. It's going to end up 1.25 times 10 to the minus 8 centimeters. And then the volume was equal to L cubed. So that's 4 times 1.25 times 10 minus 8 centimeters over the square root of 3, quantity cubed. So we could calculate that. (2.41 times 10 minus 23rd). So great, that's our volume. We need the mass of the unit cell. Any ideas? How many atoms are in the unit cell? Body-centered cubic, 2 atoms, right? The one in the middle, the body-centered one, and the 8 corners that are each 1/8. So there's 2 atoms. Can we figure out the mass of 2 chromium atoms? Sure we can. So 2 chromium atoms The periodic table would give us masses in atomic mass units, but we want grams for our density, right? So it's a certain number of grams per mole. So for chromium, it's 52.00 grams per mole. But I've got atoms, so I need to convert atoms to moles. There are Avogadro's number of atoms in a mole. And then I can use the molar mass, 52.00 grams per mole, to figure out the mass in grams of 2 atoms. It's going to be really small, but it's okay. So 2 divided by 6.022 times 10 to the 23rd times 52 So this is 1.73 times 10 to the minus 22 grams. That's my mass. I'm going to plug in up here, 1.73 times 10 to the minus 22 grams. So I divide by 2.41 times 10 to the minus 23rd, and I get 7.17. Isn't it kind of crazy that that nice number, 7, came out of all that other stuff? Is 7 grams per cubic centimeter a reasonable density for a metal? Yeah. The density of water is 1 gram per milliliter or gram per cubic centimeter. And metals are more dense than water, and so it should be higher than 1. And you could look it up. Hey Siri, what's the density of chromium?
The density of chromium is about 7.14 grams per cubic centimeter.
So, came out pretty good, huh? She doesn't always perform very well, but she did today. Go Siri. So another way to look at these crystal structures, instead of looking at the unit cells, is to look at how the layers are arranged. And you could try this at home with fruit or marbles or anything that is spherical and close to the same size. If you think about putting marbles in a box, right, and how are they going to arrange themselves in the bottom of the box? That would be the structure of a layer. And then how do you put the second layer on top? So a simple cubic structure has, let's look at this top layer. It has the atoms arranged in rows and columns. So in a grid shape, they're all just lined up with each other. That's not the closest thing. That's not what marbles would naturally do, but you can get them to do that, right? That's not the most efficient way to pack. And then putting that layer exactly on top of the next layer, on top of the next layer. And so the atoms are stacked up vertically and they're organized horizontally as well in rows. That is equivalent to the simple cubic cell. And here we have it drawn in here in the white. A more efficient packing, and this is what marbles will naturally do if you force them into the corner, is they'll pack like this, where this row nestles into that little space created by the next row. And so you can get a lot more spheres in the same area using this pattern. So this row is offset 1/2 of an atom from that row. Does that make sense? And so you can get them a lot closer that way. Then, okay, so that's the one layer. What are we going to do with the next layer? Well, the next layer, layer B, instead of trying to put the atoms directly on top of each other, which would be less efficient, we're going to let layer B be offset as well, so that the blue balls here are sitting in the little dimples created between the red balls. Does that make sense? And so we've got layer A and layer B. And then we have to ask, well, what are we going to do with the next layer? So in what's called a hexagonal closest packed is we've got layer A and layer B, just like we looked at, and then the next layer lines up with atoms directly above the first one. And so we have an A-B pattern. This is called a closest packed structure because it's how things get the closest. You get a coordination number of 12, packing efficiency of 74%. Hexagonal closest packed, and then you can also have a situation where that third layer, instead of being lined up directly with layer A, is offset. It's offset from layer B and from layer A. And so then you get an ABC pattern. This is actually identical to a face-centered cubic. Let's go back to this hexagonal closest packed. Here, if you look at the smallest unit cell, it's a hexagonal cell. So we can see here this has been cut, so it's a hexagon. So this would be the hexagon. The smallest cell here, though, is this with the trapezoid base here. So this would be the unit cell. You need to know that exists. We're not going to do any calculations or anything with that one. The cubic closest packed. So here we have, looking at the layers, you put all those together, you tip it at an angle, and you chop it up, and you get this. So this is a piece of that. And I think we can see that there's one face, and there's another face, and there's a face on top. This is the same as the face-centered cubic cell.